Welcome to the 8th lecture. We just now discussed the concept of permeability based on Darcys Law, which says the velocity of flow in soil is equal to V is proportional to the gradient. The constant of proportionality is called the coefficient of permeability. I is the hydraulic gradient, which is equal to loss in total head, please remember, divided by length, or shall we say distance of travel. For example, let's look at a simple gravity dam on soil, and I have water stored here. This is equal to H, and the water level on the downstream side is 0. Let's take the datum here, and you would like to know what will be the flow through a layer which is, let's say, 5 meters thick. And obviously the dam is very long, maybe running into 100, 200 meters or 1 kilometer. What you would like to estimate would be what will be the loss through the foundation because of storing of water of a certain height. Let's say this height is 100 meters and the base width of the dam is maybe something like 160 meters or maybe 200 meters. The total head at point A on the upstream side is 100 meters. The total head on the downstream side at point B, if I take the datum here at the base of the dam, is 0. So delta H, the head loss, is equal to HA minus HB, which is equal to 100 meters. What is the gradient? I is equal to delta H divided by the distance traveled, which is 100 divided by 200 meters. I am looking at, say for example, the closest or any 2 points if I am looking at it. Let's say I am looking at from here to here, but the shortest distance is from the toe of the dam to the heel, which is what we call as 200 meters, and I'm going to calculate based on that. So I'll get the gradient is equal to 0.5. Let's say the permeability of the soil is something like, say, 10 to the power of minus 5 centimeters per second. So the velocity of flow is equal to K into I. K is equal to 10 to the power of minus 5 into 0.5. So that gives me 5 into 10 to the power of minus 6 centimeters per second. And what will be the flow? Now the thickness of the stratum is 5 meters. Let's look at 1 meter width. Flow for 1 meter width of the dam is equal to V into cross-sectional area. Please remember, you have to look at the cross-sectional area through which the flow is taking place. So the thickness is 5 meters and the width is 1 meter. So I'm going to multiply 5 meters, of course, into 100 into 1 meter into 100, because I'm converting into centimeters. So that becomes 10 to the power of 4, 5 into 5, 25. So that gives me Q is equal to 25 into 10 to the power of minus 2, or 0.25 cubic centimeters per second. This is 10 to the power of minus 6, 10 to the power of 4, so 10 to the power of minus 2 into 25, 0.25. Now you don't calculate per second, you may have to calculate what will be cube per year per meter length, which means this 0.25 into, in a day you have 86,400 seconds into 365 days. So that will be the kind of loss through the foundation over 1 year, and you have to be very careful in estimating, because if you don't take care of that, the water in the reservoir may escape through the foundation. If the K of the foundation soil is high, all of the water may be lost. So as a geotechnical engineer, we make sure the foundation is relatively impervious. So this is how we calculate. Just to give you a full estimate here, this is 2.5 into 10 to the power of minus 1, 8.6 into 10 to the power of 4 into 3.65 into 10 to the power of 2. So you can see that 2.5 into 8 is something like 20, into 3.6 is about 75, into 10 to the power of 5, so 7.5 into 10 to the power of 6 centimeters per year. So many you convert into liters or cubic meters, you get the loss per unit length. And if the dam is long, you have to estimate correspondingly what will be the total loss. So that's how we do that. Here, I would like to mention one more parameter. When you define this permeability, does it depend on the fluid or same fluid at all temperatures? We said V is equal to K into I. This is for normally we are looking at water. If I change the fluid, will the permeability be the same? We find that K depends on the unit weight of the fluid, the coefficient of viscosity, into some intrinsic coefficient called intrinsic permeability. So please remember, this is called, this parameter does not depend on the fluid. So the coefficient of permeability depends on a soil characteristic which is dependent on the void space, the path, etc., and the fluid properties. And this is gamma W is unit weight, and eta is the coefficient of viscosity. That's another important parameter. Is coefficient of viscosity same or does it depend on temperature? You know that when a fluid is heated, coefficient of viscosity decreases and it can flow faster. So please remember that we have this problem even in soils. If you have a cold temperature, the coefficient of viscosity of water is low, and then the coefficient of permeability can be high. The same water, when you heat it, it becomes less viscous because coefficient of viscosity decreases, permeability increases. So in order to do this variation, account for it, what is done is K is defined at 20 degrees centigrade temperature. The K at T is equal to 20 degrees. This is the standard. You have to report. Fortunately, unit weight is not that sensitive to temperature. In the range gamma W is approximately constant. If I am looking at, say, something like 10 degrees centigrade to about 40 degrees centigrade. Whereas eta can vary from something like, say, with respect to eta 20, 1.1 to 0.9 times eta at T is equal to 20. So you find that we need to correct for temperature. So because it's inversely proportional, can I say K at 20 degrees centigrade is equal to K at the lab temperature into eta at T is equal to 20. It's proportional to inversely to the viscosity coefficient. So we take care of that. And just to give you an idea, if T is equal to 30 degrees centigrade, eta 30 degrees by eta 20 degrees is around 0.9. If you are doing the test in summer, when the temperature in the laboratory is around 30 degrees, you will have very high velocity or coefficient compared to what will be the temperature and viscosity at 20 degrees, which could be the temperature in winter. So when you do the test in the laboratory, please correct it for 20 degrees using this equation. Now let us see how we can determine this permeability. We can do that in the laboratory or we can do it in the field. This is called in situ. It's a common word you will see in geotechnical engineering. In situ means at the site. So we can determine either in the laboratory on a small sample, or if you are doing a big project, you have to find out what is the permeability in the field. In the laboratory, we use what they call as permeameters. The equipment apparatus that we use to determine permeability is called permeameters. We have what is called as rigid wall or flexible wall. Permeameters. If I have a cylinder made of steel or brass, compared to the soil here, this is very stiff. So the walls of the permeameter are rigid. We sometimes do it by covering the soil in a latex membrane. It's a very, very thin. If I just give you an idea, it could be, if I make a cylinder with a plastic sheet or latex membrane, like the one you use for balloons, etc., it is a very thin, highly flexible one. So then you will have a flexible permeameter. The reason why we prefer this, even though many labs don't have, is because when you have flow, the voids here allow the water to go along the wall, whereas here the membrane comes inside and there will be no flow along the edges. No flow, whereas here flow possible, may not be significant. So what you find is maybe 5%, 10% of the water will not flow through the soil, but will flow along the boundary of the permeameter. But most laboratories have only a rigid wall permeameter. So let me look at the determination using a rigid wall permeameter. We'll go later to determining permeability in the field. We have two tests with the rigid wall permeameter. One is called constant head permeability test and variable head permeability test. This is for coarse grain material, whereas this is for fine grain material. In the constant head permeability test, we take sample of soil in a tube, provide a filter paper, and then you have a mesh, and then connect it to a base. At the top, we have a reservoir, and I keep pouring water, but the water level is always maintained at a constant level. I take this from the bottom to another reservoir and maintain this level constant. Please note that the diameter of the tube is equal to D. The length of the sample is L. I maintain the water level here constant, so that if you keep adding water, it will just simply overflow. Similarly, the water that comes through, this is all the soil here. The thickness of the tube is L. And the water flows through, and this mesh and the filter paper is to prevent the soil coming down, and we connect the bottom of the tube, another reservoir, and it is collected into this reservoir. The top of this reservoir also is maintained constant, so that flow always occurs once the reservoir is full. So what we do is we start the test and collect. As you pour it, I use a measuring cylinder. It's one of those standard jars you have in the laboratory. I collect it, let's say, for 5 minutes and measure the quantity of flow Q. Q could be 400 cc, 600 cc, etc. So the test is, you put the soil, whatever condition that you think is appropriate to the field, in the sample, or you push a tube into the ground and bring the sample here, put it here, and of course you also put another filter paper or mesh on the top, so that the water flows uniformly down below, flows through the sample, comes into the bottom reservoir, and whatever is overflowing over a period of time, 5 minutes, 10 minutes, you collect it. So you will get the quantity of water collected over a given period of time. Can I say then Q, the rate of flow, is Q by T. So that is equal to, let's say, some 400 cc by 5 minutes, that's equal to 80 cc cubic centimeters per minute. So we have now the rate of flow. We also know the head loss, the difference between these two elevations. Can I say the upstream elevation, suppose I take some datum here corresponding to the bottom level, this is the net difference, this is HB, the datum I am taking right here. It doesn't matter, you can take the datum anywhere, in which case the elevation head will just get added up. Shifting the datum will not change the head difference because you are only taking the difference. So what is the upstream water level at a height H, A, and corresponding to the bottom is HB. So the difference between those two is the net loss. Please remember, this is the total head corresponding to datum at the downstream water level. And what is the total head at point B? 0. So can I say head loss is equal to HA minus HB, that is equal to HA itself, or shall I say H. Now what is the hydraulic gradient now? The hydraulic gradient is H divided by the length L. The flow is taking place through maybe say 300 centimeter, 30 centimeters, 300 millimeters or 150 millimeter length. So you get this. H by L gives me the gradient. Let's say H is equal to maybe something like the difference between these two is probably about 200 millimeters and L is 150. So you have a gradient of 1.33. Okay. Now V is equal to Q by A, or Q is equal to V into A, rate of flow over the cross section. What is the cross sectional area? Is pi d squared by 4. So velocity is equal to Q by pi d squared by 4. We know the gradient, we know the velocity. So, or you can say Q, which you found out, is equal to K into I into cross sectional area. So K is equal to Q by I into A. You have found out gradient 1.33, cross sectional area is pi d squared by 4, D for let's say 150 mm, 6-inch cylinder, you can easily calculate. So this is how we determine the permeability, but maintaining the head constant on the upstream and the downstream side. That is why it's called constant head permeability test. This can be done if I can collect enough water. Suppose I wait for 5, 10, 30 minutes. If I can get maybe 50, 100, 200 cc of water, I can measure it. This large quantity is possible only in coarse grained soils, that is sands and gravel. You can have fine sand, coarse sand, silty sand, etc. Then you can measure enough water in the jar over a normal period of let's say 15, 20, 30 minutes. You cannot wait for one day to do a test. That will be very slow, and you normally find that then the rate of flow is so small, evaporation also may take place during that period. So what we then do is change the test to what is called as a variable head permeability test. For fine grained soil, we take the same sample in the tube. Instead of having a reservoir, I connect a small tube here, and at the bottom of course we have the reservoir as before. This is the sample, length is L of the sample, the diameter is D, but this has a very small diameter, something like a capillary tube. Let's say diameter of the tube is something like let's say 1 centimeter. Please remember, this is of the order of 150 millimeters. This could be maybe 1-2 centimeters. It's like a standpipe, whatever size you can think of, a very small one. We fill it with water here, and you maintain the downstream side constant level. So can I say that at any time t, the head is h? So what we do is that we have a long tube and conduct the test corresponding to, initially the height in the tube is h1, and we wait, conduct the test till it becomes h2. The head is not constant at all times. It keeps decreasing with the flow. Because I put in a small tube, I can easily find out what is the fall or the rate of fall of the water in the small tube. Please remember, I am maintaining the downstream side at constant elevation or constant level, which means the downstream is, if I take the datum, the head is always measured with respect to the water level in the bottom reservoir or downstream side, and I can just look at it. I can put in a scale behind so that I can take the readings from the bottom based on the scale, and we can measure the elevations. At t is equal to 0, h is equal to h1, at t is equal to, let's say, 15 minutes, h is equal to h2. So I have measured the fall, and now I try to analyze what happens to the flow. It's a very simple modification of Darcys law. Let us say you have the tube here with the soil, this length is L, and the standpipe is here, and at any time t, the elevation, the total head is h. Let us say in a small time interval, the head falls by delta h. I am looking at a very small interval, could be 1 second or half a second. Then what will be the flow? Please remember, we are looking at a very small time interval. Delta t is less than 1 second or a fraction of it. Can we write the Darcys law? Velocity v is k into I. So that is equal to coefficient of permeability. I is equal to h by L. And what will be the quantity of flow? Q is V into A, which is equal to K h by L. Area is pi d square by 4, or shall we say capital A? I leave it as it is. And the water level has fallen over a distance delta h. So can I say what will be delta Q over that time interval? This is equal to Q into delta T. Isn't that equal to delta H into area of the tube? Area into delta H, where A is the area. Because A is very small, you can see the waterfall within that. So can we now say over a small interval of time delta t, the quantity of flow is equal to Q into delta t times the area of cross section of this tube into delta H. Now substitute here, Q is equal to K H by L A into dt is equal to A into delta H. Coefficient of permeability times gradient times area of cross section of the soil within the tube and the time interval delta t is equal to the area of cross section of the tube into the drop of the water level within the capillary tube. Can I simplify saying that? Can I write delta H by H and bring all other terms here? And also I would like to put in here H is falling, so it has to be a negative. So I'll write it as dt is equal to L into small a by K into capital A. And why we take the negative is because the head is dropping. I still want the gradient to be positive. So if I take that, I can separate out the two variables. I have the small interval delta t, and you have dH by dt with a negative sign. Can we integrate this now? T1 to T2 dt is equal to L, the length of the sample through which flow is taking place, area of the small tube by coefficient of permeability, and area of cross section, you know how to integrate the two terms. So this becomes T1 minus T2 is equal to L into A by K into capital A, and you will have log to the base C of H, because with a minus sign, H1 to H2. At T is equal to 0, the height is H1. At T is equal to T2, height is H2. So if you simplify this now, T2 minus T1 is equal to, please remember there is a negative sign, so I can take H1 by H2. You will get L into A by K into capital A log to the base E H1 by H2. And it will tell you why, because once H is falling, H1 is higher than H2, so this will be a positive ratio more than 1, so that the log of a positive number is greater than 0. You don't want to get a negative 1. This is to the base E. When you integrate derivative of H with respect to H, can we convert that into base 10? So that becomes 2.3 L into small area log to the base 10 H1 by H2. So to determine the permeability from variable head test, from this you can get K is equal to 2.3 length of the sample, area of the capillary tube by, you start the clock, measure the elevation here. After 5 minutes or 10 minutes, take the elevation again, you get H2. So you know the time interval could be 5, 10 or 15 minutes. All the parameters are known. You know the length of the sample, area of cross section of the tube, you know the total cross sectional area of the sample and the measured time, and the two heads H1 and H2. And that's how we determine. And you can now find that even very small permeabilities can be measured, because the smaller the area, this ratio is very small. Look at this. If I have 2 centimeter diameter and at 15 centimeters, the ratio is 4 by 225, so I get a very small value.